Now, some of you might have already seen the notion of topological entropy somewhere else for a dynamical system. What is the relation between our definition of topological entropy here and the usual notion of topological entropy for a dynamical system? Although this is not an essential part of this lecture series, let me briefly explain this to you. Relation to the usual topological entropy. Now recall the usual definition of topological entropy for a compact metric space. Recall for a compact metric space x, d and a continuous transformation t from x to x, we define a new metric Dn as follows. For any xy in x, Dn of xy is defined to be the maximum for I from 0 to n minus 1 of the distance between ti of x and ti of y. So this metric measures the maximum distance between the orbit of x and the orbit of y under the action of t in the first n stages. The 0 stage is just the x and y. With this metric, we define a quantity fix epsilon greater than 0. Let curve n epsilon t denote the minimum cardinality of a covering of x by the sets of Dn diameter less than epsilon. Using notations, this means curve n epsilon t is the mean of this set K such that there exists xi, I is from 1 through k, such that x is a union I is from 1 to k, this diameter with respect to the Dn metric here, that means the supremum of distances for any 2 points in xi. Less than epsilon. The reason that we can make this cover to be a finite cover is that we assume this x to be compact. So we can always choose those xi's to be open, and because of the compactness, we can reduce the cover to a finite cover. So this number must be a finite number. and it suffices to consider the finite coverings. And now, if you look at this quantity, the logarithm of curve n epsilon t divided by n. It turns out this limit exists, and it's finite. And we define the topological entropy of this dynamical system to be the limit as epsilon goes to 0 of this h epsilon of t. This h epsilon of t increases when epsilon decreases because of this definition of covering numbers. So this limit makes sense. So this guy is called the topological entropy of the dynamical system x dt. So how is this notion of topological entropy of a dynamical system related to the topological entropy of bounded sequence? So now let me tell you the relation. The relation is the following. If you consider for a bounded sequence of complex numbers, that x sub f is a closure of this sequence, starting from the second term of the sequence. Because the sequence is bounded, its closure must be compact. So this is a compact subset of C. Equipped with the Euro distance in C. And we consider transformation T that sends f of k to f of k plus 1. And we extend this continuously to the closure x of f. Then, for two integers n1 and n2, dm of f of n1 plus 1 and f of n2 plus 1 will be just equal to, so by definition this is the maximum, and this, if you write this out, it is the supremum norm of this. And now you can define this covering number, cup n comma epsilon comma t. Note that for this definition, we are using the diameters. But for this definition, for the topological entropy of sequences, we are using the radius. But this doesn't matter, because radius epsilon just corresponds to the diameter. And this difference does not matter, because in the end, we are considering for this definition for any epsilon greater than 0. And for this definition, In the end, we are taking epsilon goes to 0. And now, if you are comparing the definition of entropy in this setting and the definition of the entropy we defined at the beginning for bounded sequences, the sigma appearing here can be obtained by first taking the log so that you can drop this exponential function, and then you divide by m. Because this part is little omega of m, it will go to 0 when you divide by m, and then m approaches infinity. That is exactly going on in this definition. You take the log and you divide this, divided by n, which is m in this setting. So for a bounded sequence f, if we consider this space and this transformation, the topological entropy for this topological dynamic system is precisely the least sigma such that the vectors can be covered by this many balls of radius epsilon. The implied constant here, remember, is depending on epsilon f. This is true for any epsilon greater than 0. So those two definitions are equivalent. If you identify this bounded sequence with this topological dynamical system. Just in case some of you might want to see a formal proof of this, let me show you the formal proof. We're going to show the topological entropy of this T is same as the sequential topological entropy of F. First, let us see why the left-hand side is less than or equal to the right-hand side. Let's prove this inequality. Suppose for any epsilon greater than 0, there exists big omega of exponential of sigma m plus little omega of m, many balls of radius epsilon covering this sequence as m goes to infinity. Now let B1 through B alpha of m be those balls. So it follows that alpha of m is less than or equal to some constant c that depends on epsilon f times the exponential of this. Now let pi 1 be the projection from Cm to C denote this projection onto its first component. Then if you look at pi 1 of B1's closure, all the way through pi 1 of B alpha M closure, those closed balls in C, one-dimensional in C, will form a covering of XF with respect to the M metric. And if you look at the covering number curve M to epsilon T, here we use 2 epsilon because radius epsilon corresponds to the diameter 2 epsilon. When we define this, we are considering the diameters rather than radius. So we have to make this adjustment. From our construction above, this guy will be less than or equal to alpha of M. So it follows that H epsilon of T, remember this by definition is a limit as M goes to infinity of logarithm of the curve M to epsilon F divided by M, which is less than now I should use lim sup log of alpha of M divided by M, which, remember, alpha of M has an upper bound. So this is further bounded by. Now, if you write this product as sum after applying a logarithm function, this will end up giving you just sigma. This part, this little omega of M, taking exponential, taking log, divided by M will go to 0 as M goes to infinity. This is a constant. Logarithm of this constant divided by M will also go to 0. The only thing that is left is logarithm of exponential of sigma of M divided by M. That is just sigma. And now, if you take the limit with respect to epsilon, we obtain the topological entropy of this dynamical system is bounded by sigma. And now we let this sigma approach its infimum, which yields this inequality. So this proves this direction of inequality. And now let us check the other direction. So now we want to show that the topological entropy of the sequence is less than or equal to the topological entropy of this dynamical system. So now recall from the definition that topological entropy is of the dynamical system is this double limit. Because this covering number increases as epsilon approaches 0. So this limit is the same as the supremum. Then, for any epsilon greater than 0, we know this limit is less than or equal to h top of t. This tells you for any eta greater than 0, there exists a capital M such that for any m greater or equal to this capital M, log is bounded by h top of t plus eta. And this further tells us if we move this m to the right hand side and take the exponential on both sides, this gives us curve m epsilon t is less than or equal to exponential of m h top of t plus eta for m sufficiently large. But recall the definition for the covering numbers. In the definition of covering numbers, this curve denotes the minimum cardinality of a covering of X by the sets of diameter less than epsilon. But we have to change this to the language of balls. So here is the elementary geometry. If you have any set, any shape of diameter less than epsilon, then this guy can be actually contained in a ball of diameter 2 epsilon or a ball of radius epsilon. It follows from this geometric relation that there exists big O of exponential of m times h top of t plus eta many balls of diameter less than epsilon with radius less than epsilon covering the sequence. So this just follows from the definition for the curve n epsilon t and this elementary geometric fact. This tells you, so look at this big O exponential of m times this guy. The infimum number, namely the sequential topological entropy of F, must be bounded by h top of t plus eta for any eta greater than 0. So h sig f is less than or equal to h top t. And this finishes the proof.